Hi everyone, welcome back to Physics 11. So in this video I'm gonna go over some of the questions that people ask me to from the spring worksheet, so Hooke's Law worksheet 5.4. Now my solution isn't gonna differ much from the solution that's already attached, but perhaps it will help you understand the question a little better. So number 5 says a spring is 20 centimeters long, and when you apply a load of 10 newtons vertically, so basically we have perhaps it's hanging from it, or it could be another case where it's compressing it. In this case it's hanging from it, and there's again it's 30 centimeters long when you apply a bigger load of 20 newtons. So we have two cases here. So let's make a free body diagram for each case. So for a load of 10 newtons, we're going to have a mass, which is our spring here. Let's say this is the mass from a spring. And then we're going to have two forces acting on this body, right? So let's say we already know what the force of gravity is equal to. So the 10 newtons, because it's hanging from it. So this is our Fg here. And then the other one is going to be for the other case. So these are our forces of gravity acting on them. And we're going to have the restoring force, which is the spring force here. So this is going to be our F spring or elastic, Fe. Right? So we already know the Fg value here. In the first case, it's going to be 10 newtons. Okay. And same idea really applies to the other case too. We're going to have, again, the same two forces acting on it. The only difference again is that the Fg is bigger. So if you can make another free body diagram here. So let's make this here for 10 newtons. So let's say Fg equal 10 newtons, and this one Fg equal 20. So let's make another. And that's going to be our Fe there. So let's make it positive to be up. Those are the two free body diagrams for the two different Fg values. Now the F net equation in this case, it's only in the y direction. So let's do one for the first one, and really this is going to be the same for both of them. In this case, we have our Fe minus the Fg equal, well, you can write m times acceleration in the y direction, but it's going to be 0 because it's at equilibrium, so it's not moving up or down, so there's no acceleration, so this will be 0 here. So that leaves us with the following: Fe minus Fg equals 0, and therefore these are going to be equivalent. So the spring force or the elastic force will equal to Fg. Now let's expand our Fe force, which is going to be our delta x times k. Now the force of gravity we don't need to expand because it's already given to us, so we don't need to write m times g because we just have the value of 10 newtons or 20 newtons. So we're going to leave that as Fg. Now the thing that we had to figure out is the delta x here. So we need to expand the delta x for each case. So for this one, we're gonna say that let x at equilibrium, basically when the spring is unstretched, equilibrium position for the spring. Okay, and this is going to be the same x eq for both of them because the spring is the same, it's just different forces that are acting on it. And then the other is going to be our x. So x is going to be the length of the stretch spring. So in case 1, so this is our case 1, case 2. In case 1, it will stretch a little less, okay? And it says here 20 centimeters. And in case 2, will stretch more. It'll be 30 centimeters long. So as you can see, it stretches 10 centimeters more in the second case. So let's expand then our F net equation a little further. So then we can say our delta x is going to equal the x minus the equilibrium value, because it's going to be longer. X is going to be longer when it's stretched. The equilibrium is going to be the shorter value, so we're going to get our delta x that way. You can also really flip them around and just take the absolute value of them, but in this case we don't need to do that. So let's add that into our F net equation. Let's expand our delta x as the x minus x equilibrium equal to Fg. So again, F net equation is going to be the same for both of them. The values are going to be different for the x value, right? So one is going to be a little longer than the other. But again, we don't know the actual value of either x. We know the x. We don't know the x equilibrium. So let's write the two equations for each one. Okay. So let's write the F net for each case. So this is the overall equation we're going to use for both of them. So let's write the two equations. Now in your solution that I attached, they use L instead of x, but again, same idea. So length for the spring. So in the first case, we're going to end up with this equation. So for the 10 newtons, our equation is going to be K. Now in the first case, the spring stretched 20 centimeters, which is 0.2 meters. So make sure you change that to meters minus the x equilibrium. And the force of gravity is 10 newtons. Okay? So again, this is your x. You can call it x1. And then for the other case, so number 2 for the 20 newtons force, we will have a very similar equation. The only difference again is going to be the stretched length. Our x value is going to be 30 centimeters, which is 0.3 meters. So make sure you don't forget to change this to meters. And this equals to the force of gravity of 20 newtons. So here we go. We got two equations, right? But notice here that the k value and the x equilibrium is unknown. So we have two equations, two unknowns, which is fine because we have enough equations to solve for both unknowns. So the next step is to use substitution to solve it. Now what you can do is expand this, solve for one of the variables, let's say k, or for x equilibrium. Doesn't matter which one you solve for. So we have again system of two equations. With two unknowns, which in this case are k and x equilibrium. Now notice the x equilibrium is going to be the same because again it's the same spring, because it will return to the same position once it's the force of gravity is no longer there. So these are going to be the same. The k, the spring constant, and the x equilibrium are going to be exactly the same. That's why we can actually write the system of equations. Otherwise we would need a third equation if the x equilibrium were different. Now, like I said, you can use substitution. So solve one of them for one of the variables. I'm going to solve the first one for k. I need to move this. So let's do this in different colors. So here's our first equation. Let's solve this for k. So all we have to do is divide both sides by 0.2 minus x eq. So K is going to equal 10 newtons over 0.2 minus xeq, right? So that's our equation 1. So what we can do next is take this equation for K, plug it into equation 2. So our next step is going to be substitution. And this might take a few steps here, but let's take our second equation and plug it in without changing anything. So our equation 2 here, we're going to take the value for K now, we're going to replace it in. So again, our K now is 10 over 0.2 minus xeq. All right. Now I'm using the second equation here, so 0.3 minus xeq equal 20. So it looks like quite a messy equation here, but we need to basically rearrange this so we have everything in one line, so we don't have any denominators here, and then solve for xeq, which is the only unknown, but it appears in both the denominator and the numerator, so we need to do some algebra here. So let's see what we should do next. It's multiply by 0.2 minus x equilibrium, so we bring it up to the numerator, which is going to leave us with 10.3 minus x equilibrium equal to 20 times 0.2 minus x eq. All right, so that's the first step. We multiply both top and bottom by, well, not really, just multiply both sides, not divide. Both sides by 0.2 minus x eq. We get this. Now we can have to expand each of these. So multiply this out. So 10 times 0.3, which is going to be 3, minus 10x. 2 times 0.2 is 4, minus 20x eq. Move all the x's to one side, the constant to the other side. So in this case, I'm going to bring the negative 20 to the left, so it becomes positive. So I end up with 20 positive x minus 10 and the 3 to the right, so it becomes negative. So I'm left with 10 x eq, and on this side I just got 1, which means that last step is to divide by 10 both sides, and we get x eq equal 1 over 10. Which is 0.1. And in this case, this is meters. So that's our first value that we're looking for. We found our x equilibrium. So we know that the spring will return to 0.1 meters in length, so basically 10 centimeters when the force is removed. So this is 10 centimeters here. So that's pretty much most of the work is already done here. The last thing we need to do is find the k value. So don't forget about the k. So we can go back to the first equation, the purple one, and plug in our xeq into the first equation and solve for k. So for k, remove this. All right, so for k, we need to take our equation for k, 10 over 0.2 minus x equilibrium, plug in the value that we found, 0.1 meters, right, for this, and we can solve for k. 0.2 minus 0.1, so again, remember it has to be in meters, so even though I solved for centimeters here, we had to use meters in the equation, and we get 10 over 0.1. Right, so that's gonna be our spring constant. So 10 divided by 0.1 is gonna be 100. All right, so that's gonna be our question number 5.